Okay, at first I would like to give the thanks to the organizer of ICTS and the Indian Statistical Physics Community to give me the opportunity to speak here. This is the title of my presentation today, and this is my affiliation, and also this is the acknowledgement in the library Ramon Research Institute. If the Ramon research not help me, then my research will be reduced to the 1/3 what I used to do. The outline is as follows: introduction, a few words on the basic aspects of the model, Hamiltonian results and the conclusion, a few words on the quantumizing model. All of you here in the audience know that is this quantumizing model or Ising model is the master degree. In the 1922, Lenz, the thesis supervisor of the Ising, he is the problem and Ising solved it. 1925, exact solution by the transfer matrix. So solution was very simple, but he has not found any transition from the paramagnetic phase to the ferromagnetic phase or the vice versa as a function of temperature. But on the other hand, in the two dimension, the interaction became too complex to solve. But in the two dimension, they can find the solution. After getting this result, Ising became very frustrated and he migrated from the Germany to States, and he started to work in this way in his office. And when the exact solution come and the phase transition find 2D, again he work as one working normally. The motivation of this work is this: the physics of quantumizing models started extremely literature, but the quantum field theoretical aspects is still today not up to the mark. I would like to come to this point in detail. This model Hamiltonian, the whole time is solving from the perspective of the topological phases, but the main motivation is to explore the physics from the perspective of the correlated quantum any-body physics. And particularly, I would like to see this is the RG equation, quantum field theory RG equation. My RG equations are as exact as possible. Something to say, you know, the first two, each term is the transverse term, transversizing model or quantum fluctuation introducing each term, and each term nothing but the ferromagnetic interaction term, and these two terms in the competing. All of us know textbook, many material in the, as I know, in the India, depending on this first two terms, there are 3 books, but I don't want to quote the name of the authors. But the thing is, this is the 3-spin interaction. This interaction is very peculiar and interesting. Kindly see here, I-1 and the I+1, nearest and next to next nearest is the ferromagnetic coupling, but the inside it is giving the quantum term. And if you consider the nearest and nearest term, they are giving the exact coupling. I call this interaction as a 3-spin interaction. And also I would like to show you another presentation of this model Hamiltonian you can find there. Also, one can solve it from my model Hamiltonian, how I derive this Hamiltonian. This is the detailed derivation of the calculation, and this is the unitary transformation of this Hamiltonian. I call this Bostonization Hamiltonian, means after the quantum field theory calculation, but indeed this is called the correlated quantum Ising model Hamiltonian if we consider the first 3 terms. And this is the 3-spin interaction. If you see, that is this quantumizing model. In the quantumizing model, you will find the lambda1 and the u2, and but there is the factor k will be absent in the quantumizing model. Then the question is how the k is appearing. K is an emergent term, is appearing in the Hamiltonian, and this is I call the correlated quantum Ising model or the correlated quantum extended Ising model. To the best of my knowledge, 1925, Ising has defined this term. 1952, QT has defined this term, but the correlated quantumizing model, that is the first time in the literature I introduced and also solved by using quantum field theory calculation. And now the question is how I get this A term. if I can express the spin operator in terms of this by using this quantum field theory calculation, I have derived this calculation, and K is an emergent parameter. K less than 1 means the system is the strongly correlated phase, the repulsive phase. K greater than 1, system is the attractive. K equal to 1, the system is the non-interacting term. And the effect of the strong correlation on the quantumizing model and the longer range quantumizing model, I will take through this parameter. I call this Latin liquid parameter. Actually, I would like to solve this Hamiltonian. Those who are aware of the quantum field theory, they know this type of Hamiltonian is called the Sine-Gordon Hamiltonian. But my last, this type of term called the Sine-Gordon Hamiltonian, but my things are more complicated. It's the theta field and phi field at the world field. The derivative of the field and this is related with the Heisenberg uncertainty commutation relation. And this dual field multiplied by this the augmented kinetic energy term, the system became more and more complicated to solve. And I take this ln how to solve this hard equation as exact as possible. Let's see how I solve this equation. And so I can solve this equation by using the quantum field theoretical renormalization to study. Why I do? Only for the fascinating hard mathematics? No. That is the but I forced to do because here the mu lambda 1 and lambda 2, all the coupling terms are related with each other, and the minima of theta and phi coupling are the same. So to get the correct picture, only the dimension and analysis is not the correct picture. One, I must have to be do, that is this RG flow diagram to get this. And this is my quantum field theory RG equation. This is the quantumizing model RG equation. This is the extended quantumizing model with 3-spin RG equation. And this is the both lambda 1, lambda 2 term in the absence of the transverse field or the quantum thing. At first, I would like to benchmark my result. Benchmarking with respect to the standard result of the quantumizing model. It's in the book, in the literature, in the monograph. So we know that it's the coupling it at G. When G much greater than 1, the system is the quantum fluctuating space, either any one of the state. But when the G less than 1, system is in the ferromagnetic states. Let's see whether I can get this. I solve this RG equation for each case, and if you see this RG equation, here the K equal to 0.2, 0.5, 1, and 1.5.
2 plus 2.
2 minutes, okay. Now the thing is this here, when the lambda 1 in initial value is large, the system is going to the ferromagnetic phase. But when the initial values of mu is larger, the system go to the quantum spin disorder phase. So here there is a transition. Here there is a transition as we observe in the quantumizing model. So quantumizing model benchmarking the results for the strongly correlated phase. But when I go to the non-interacting and also for the attractive phase, the system is that there is no phase transition. System is always in the quantum disorder phase, means this is a U term dominated. So to check this, how far this is valid, so I check it explicitly up to K equal to 0.9. I found the system is still showing the same behavior. So now the question is this, now in this case, I have not considered any 3-spin interaction term. Now I consider the 3-spin interaction term for the different values of K and lambda 2. And I will see that here the system is like this transition. But in this case, you will see the both lambda 1 U are increasing same way. So I call this is the coexisting phase. This is the first kind of the coexisting phase. But in the strongly correlated regime, for presence of lambda 2, I am finding the system is a quantum spin disorder phase. So the 3-spin interaction driving the system still in the correlated regime to the quantum disorder phase. This is the effect of it. I know the answer is why it is doing but small space. 2 minutes. Okay. So here I consider the lambda 1, lambda 2 term in the absence of u equal to 0. I found here also the coexisting phase. I call the disorder phase 2. And here in this case, I call the quantum disorder phase 2 because the lambda 2 free spin interaction is going on. Here, the lambda 2 u, that is the free spin interaction and the amicus solid transverse field, they are always the friend of each other, hand to hand, and they are going on. This smoothly they are going on. And also I have done the detailed scaling analysis of this calculation, and also free scaling relation I have found, and also this all results for the different values of k from the correlated phase, uncorrelated phase, attractive phase, and this result is consistent with these things. So result, we have found two emergent quantum disorder phase. One is due to the transverse field, other due to the free spin interaction. Three different kind of phases due to the strong sources: coexistence of the transverse field and ferromagnetic coupling lambda 1, coexistence of the ferromagnetic coupling and the free spin interaction lambda 1 and lambda 2, coexistence of spin interaction and transverse field, that is the lambda 2 u, and we derive the three scaling relation for our model Hamiltonian scaling theory. Result is consistent with conclusion is the thing. Thank you. Just only one unit I would like to take. If you see here, that is this case, sorry. Okay. This is this case when they found, this is the case, Ising model, the first term. This is the term, Ising has not found any transition. But in quantum field theory, I have already shown there is a transition. But this transition is the topological quantum phase transition. And the whole audience, all of you know, the quantum Berezensky-Kosteles-Thouless transition. I have found it both the quantum Berezensky-Kosteles-Thouless transition and also the reverse of it. And also I have done detailed field theory fixed point analysis calculation. But in this short meeting, I am not presenting here. Just 1 hour before, I heard from one of the honorable speaker in month of December, Kolkata Stat Physics meeting from 20 to 23. I don't know whether I get opportunity or not. If I get opportunity, I will present this detailed quantum field theory result. 72 years, not 1-2 years. 72 years this result is absent. And my all calculation as exact as possible. Yeah, here is the end of the session.
Now we are open for questions. Okay, so there is no questions. So let us thanks to the speaker.